This is a relatively short session on Maxfilter, just to give you an idea of what it is and what you can do with it. It's short for Maxwell filtering, so it exploits some of the mathematical principles behind the distribution of magnetic fields. Its main purpose is to suppress signals that come from distant sources. So ideally, it should act like a perfect magnetically shielded room. And it should suppress everything that certainly comes from outside the magnetically shielded room, but ideally everything that comes from outside the sensor helmet. And it should still leave everything that comes from inside the sensor helmet, presumably from the brain, intact. And it only applies to MEG. So if you're only using analyzing EEG data, then this might still be interesting to you, but I don't think it'll be that useful. I could scare you with a little bit of mathematics behind it, but the main idea really is that the method exploits some properties of Maxwell's equations. So you can describe magnetic field distributions quite well with spherical harmonics, and that allows you to decompose the signal into components that come from the inside of the sensor helmet and the outside of the sensor helmet. So it's another decomposition of the data into basis functions that can be useful in order to decide what's good and what's bad in your data. And the way I would like to illustrate is a bit like that. So, well, if you model the head as a sphere, which in this case is okay, then you have the sensor helmet around it. And the basic idea is that fields that come from far away, from sources that are far away, at least relative to the distance here of the sensors to the brain, will have a different distribution than usually lower spatial frequencies, for example, than the patterns from sources that are close by, that are inside the brain. And these equations exploit that in a more precise mathematical way. And once you've got your decomposition into all these different components, the inside component and the outside component, and there's always a bit of noise around as well, then you simply remove the outside component, you keep the inside component, and hey, you've got cleaner data. That's a brilliant idea, and it usually works quite well. So this is just to illustrate from some previous papers that if you don't use Maxfilter, you can have noisy data. If you then use the what they call signal space separation, so basically two signal spaces, the inside, the outside space, and you just keep the inside space, then your data will be cleaner and you can actually see the evoked response much better in this case. Also, if you look at these topographies, if you look at a field map here, magnetometer data from the left, it looks quite speckled without the signal space separation, and it looks much better, clear dipolar field here with the signal space separation. So if applied correctly, it really cleans up your data. It has some other functionality as well that you may or may not decide to use. I mean, first of all, and that's behind the name of the software, it's the so-called software shielding. I mean, as I said, it acts a little bit like a shielded room. I mean, that's the idea, at least, to get rid of everything that comes from far away. So this is the SSS functionality of this method. But you can also then detect bad channels with it. So once you have this decomposition into your inside and outside components, the software can detect if there are some MEG channels that just don't really fit with this decomposition, that look a little bit different from other channels. And you can then mark them as bad, or it automatically does that for you. It also has a so-called spatio-temporal extension of this SSS method. Because the original SSS method alone might remove or suppress some of the artifacts that come from maybe a few meters away, but some of these components may still stay within the data, so it might not work perfectly. And what can you do to remove these remaining artifactual components? Well, there might still be a temporal correlation of these outside components with the inside components. So you can check whether if you take the outside components and you take the time course, I mean, they have a time course, like every component in this case, you can, just like with an ICA, for every component, you can look over time, how much does this component contribute to your signal? So if these outside components still correlate above a certain degree with some of the inside components, and you can conclude from that they are still an artifact included in your data. And you can use this correlation in a clever way to with an additional processing step to clean your data even further and remove these components that still have a temporal correlation with the outside components. So that's usually our standard here in our lab. So you also have a notch filter in the software, which I don't think is necessary at this stage. So you can notch filter your data, remove line noise at a separate processing step. More importantly, you have once you have your decomposition into these spherical harmonics, you can use them to interpolate or extrapolate your data. So you can compute them with the sensor positions that you have for individual participants. But once you have these spherical harmonics, you can recompute your data at different sensor locations. It is basically like interpolating or extrapolation. And that helps, for example, if you want to average data across participants for MEG, and unlike with EEG, where you have relatively standardized electrode locations, every participant will be positioned a little bit differently in the MEG under the MEG helmet. So if you then want to compute an average and remove the variability across your participants, you can use this particular function in Maxfilter. It can also help you to align different sessions for the same participant, because participants unfortunately sometimes move during the course of an experiment. For example, during a break, they might stretch a little bit. So Maxfilter can help you to remove or reduce that variability even within participants. It can also give you the actual positions of your participants for different sessions, for example. So that's something you can use to check how much your participants have moved. And that's also the case for the movement compensation functionality. So you can do something very similar, more or less often we do that every fifth of a second during a scan. So we measure the head positions. You can then compute these decompositions sample by sample, and you can use that to compensate for every movement that participants may have done during a session. So let's say they slouch down within the 10 minutes of a scan a little bit, let's say by about a centimeter. So you can make sure that in the end you interpolate your data such that they look like they've always come from, let's say, the average head position or the initial head position or sensor positions of that particular participant. It also produces the corresponding movement parameters. So you can get, for several times per second, the actual positions of the head of the participant within the helmet. And that will also allow you to later check how much your participant has moved. And this can be particularly useful if you then want to compare different participant groups, for example, controls versus patients, and maybe you're afraid that your participants move more than your controls. So you can check that with these movement parameters, but it also offers you a method to actually correct for that, or at least compensate for that. So movement compensation usually works quite well. So with the standard settings in this case, they recorded data from a stable subject and they fit dipole here. If they then make the participant move during the experiment and they use the standard averaging, you can see that it's smeared out, the amplitude is decreased, the topography is a bit more widespread here. But if they use movement compensation, then you get something that's at least closer to the original stable subject. So usually this works quite well, and it definitely gives you a good way of also checking whether movement actually has occurred in your data. Thank you very much.